Hi, this is the AP Calculus BC review video, and today we're going to be going over CPMs 3.1, 3.2, 3.3, and 3.4. So right now is 3.1, which goes over differentiation, power rule, limits, and all that good stuff. Alright, so here we have a random function that I decided to draw, and our function's in yellow, and I'll just make up a random question. Find the slope at this point right here. This point, let's say, is 4. So it might be kind of confusing at first because to find the slope of something, we need 2 points, right? We just do change in y over change in x between those 2 points, and we get the slope. But here we're only given 1 point. So how can we find the slope? Well, what if we just take a point really close to this point in red right here? I'll do this in white. All right, this is going to be called a secant. So I connect these two together, and this is an approximation of the slope on point 4 when x is 4. But this is also kind of inaccurate, right? It's not really the slope at point 4. So I'm going to erase this. I'll get rid of this. And what if I choose a closer point? I choose this point right here. This is a closer approximation. Looks something like this. But it's still not exact. So I'll get rid of this sign. I'll draw an even closer point. I don't know if I even can. Alright, right here. This looks like a really good approximation of the tangent line at this point at 4. So what did we do just now? We basically just chose points that were closer and closer and closer to the red point right here. So let's write this, but as a function. All right, so say this function is called f of x. What we did just now was, given some difference at h, we basically just made up our own y value, f of x plus h, and we are saying these are our 2 points. So this is point 1, point 2. And we take the slope of this. So this would just be f of x plus h minus f of x over x plus h minus x. Right, this is change in y over change in x. And then simplifying, we get f of x plus h minus f of x over h. All right, so we already defined h to be a very, very small difference in, so the difference between this red point and this white point, the difference of that is h. We already defined that. And as we saw, h is just getting closer and closer to 0. Now this kind of is similar to a limit. So we can write the limit as h approaches 0 of this ratio would give us our slope. So this is what the formal definition of a derivative is. A derivative, as we know, is the slope of the tangent line to a point. So basically, the slope of this blue line right here is the derivative of this function f of x at point x equals 4. So this is what's known as the formal definition of a derivative. I can pick any point x, and the difference of h will approach 0. And that will give us the slope of the tangent line to that point at x. All right, so this question is asking us to find the slope of x squared, f of x is x squared, at x is equal to 3. So here's my horribly drawn graph of f of x is x squared. Here's point 3. So basically, we want to find the line tangent to x squared at x equals 3. So that looks something like this. And we want to find the slope of this. All right, so we learned that the formal definition of a derivative would be f of x plus h minus f of x over h, and then the limit as h approaches 0. Now, do we know our x? Yes, we do. It's 3. So we basically can turn this into limit as h approaches 0, f of 3 plus h minus f of 3 over h. And now we also know what f of x is, right? It's just x squared. So we can simplify this further. F of x is equal to x squared, so this should just be 3 plus h squared minus f of 3, which is 3 squared, over h. Now this simplifies to 9 plus 6h plus h squared minus 9, because 3 squared is 9, over h. And here we can see this, a 9 and 9 cancel out. Limit as h approaches 0, 6h plus h squared over h. And now we can get rid of some h's. This h and this exponent goes away, and we are left with the limit as h approaches 0, 6 plus h, right? Because we canceled out the h here. And then now we know that h is approaching 0. We could just use direct substitution, and we have 6 plus 0, which is equal to 6. So the slope of x squared at x is equal to 3 is 6. All right, this next question is asking us to find the slope of f of x is x cubed plus 1 at x is equal to 4. So here I can draw my tangent line. This is at x is equal to 4. And we want to find the slope of the sine. So I can use the formal definition of a limit again. Limit as h approaches 0. Right, and then we know what f of x is, so we can just plug all of this in. Actually, I'll do this on the right side. X cubed becomes x plus h cubed, and then the plus 1 is just plus 1, minus f of x, which we know is x cubed plus 1 all over h. And now simplifying, we have limit as h approaches 0. And then x plus h cubed, we can use our Pascal's triangle to find the coefficients 1, 3, 3, 1 right here. And then we get x cubed plus 3x squared h plus 3x h squared plus h cubed, all minus x cubed, and then this minus 1 over h. This becomes limit as h approaches 0. We can get rid of these x cubes. We can get rid of the 1s. Oops, I guess I forgot to add that. Well, I'll just add it here. We're left with 3x squared h plus 3x h squared plus 3, or plus h cubed over h, which gives us, we can cancel the h's out. This becomes this. All right, we get 3x squared plus 3xh plus h squared. And then now we can use direct substitution. H is 0. So this becomes 0, this becomes 0, and we're left with 3x squared. but we want to find it at x equal to 4, so we can just plug in 4, and we get 3 times 4 squared, which is equal to, or 3 times 4 squared, which is equal to 16 times 3, which is equal to 48. Alright, this rule right here is called the power rule, right? Because we're changing the power of ax to the power n. But the power rule does not really work in all cases. For example, how do we differentiate sine x, or cosine x, or tan x, or even like the reciprocals of this? So cosecant x, secant x, cotangent x. How do we differentiate all these? So you could use the definition of a derivative, and you could do sine of x plus h minus sine of x over h, limit as h approaches 0. But it's going to be kind of hard to plug in 0 for h because we cannot simplify the top. So we'll just plug in a value really close to 0. We have sine x plus 0.00001 minus sine x over 0.00001. But this will be a hassle, so I will just tell you what the derivatives are. But I recommend graphing these and seeing why these are the derivatives. Before I do that, I like to define something called Leibniz notation, which is basically just d over dx of some function f of x, which just means the derivative of f of x, and this is usually written as f prime x, f prime. It's like an apostrophe. Alright, so here are all the derivatives of sine x, cosine x, tan x, cosecant x, secant x, and cotangent x. Alright, so now we're going to look at derivative functions and what they look like. So this question asks us to sketch the derivative function of this graph. So we know that the derivative finds the slope, and the derivative function, or using power rule, or finding the derivative of a function, is basically the slope function. So we could just do that. Position gets higher and higher and higher, but the slope decreases. The slope gets close to 0. So it looks something like this, until it reaches this point where it hits 0, and then it starts to decrease. The slope decreases, it becomes negative, and then it increases again kind of, and hits 0 once again, right here. And then it starts to gradually increase. And then here it starts to decrease. So we're going to reach this point, decrease until we hit really close to 0 and then 0. So this is what the derivative or slope function should look like. Now, there's something called an acceleration function. This would be a velocity function. Now there's something called an acceleration function, which is basically just the double derivative of the position function in blue, or the derivative of the velocity function, which is in green. And I'll just mark endpoints here. So we could just take the derivative of the green function, and I'll just put it in white. So here we can see that the slope is negative, and it increases to 0. So we have a negative slope somewhere around here, I'll say, and it increases until it hits 0 at x equals 0. So it increases, it hits 0, and then the slope increases. Slope increases, and then it hits 0 at this point right here. So I could say that maybe it switches to negative slope right here, so I went too far. comes back down, hits 0, and then the slope decreases again. But it gradually comes back close to 0 until it hits 0 right here. Just erase this small little thing. Alright, so here we have our acceleration function and our slope function. So the derivative, we'll call this blue function f of x. Derivative of f of x would be f prime of x, which is the velocity function. I'll actually do the respective colors. So we have derivative of f of x is equal to, and then in green is f prime of x, and then the derivative of f prime of x is equal to, in white, f double prime of x, which is the derivative of the derivative. Alright, now let's go beyond this. We have the graphs of the acceleration function and the velocity function and the position function. Now let's let's describe the position function as increasing, decreasing, concave up, concave down, where it's concave up, concave down, etc. So there's a few things that you should know. When f double prime of x is positive, f of x is concave up. When f double prime x is negative, f of x is concave down. Similarly, when f prime of x is above 0, is positive, f of x is increasing. That makes sense because it's a positive slope. And when f of x is below 0, or f prime of x is below 0, then f of x is decreasing, which makes sense because the slope is negative. And we can define a point of inflection when f of x changes concavity. And then when does it change from concave up to concave down? Basically when f of x, or f double prime of x, changes from positive to negative or negative to positive. So f double prime of x, positive to negative. This would basically mean you have a positive concave up, and then you change to negative concave down. So this is going to be, I'll just put up to down. And then f double prime of x, negative to positive. This will be down to up. So these are points of inflection. I'm just using this small sketch here. This point would be the point of inflection. As you can see, this is concave up, and this is concave down. And this point is where it switches from concave up and concave down. Alright, now to describe the concavity and all the description of this function. So we'll do concavity first. I'll just position it here. When is the blue function concave up? I'll just write down concave up. Was basically when f double prime of x in white is positive. So that's, we'll call this 0, we'll call this maybe 4, we'll call this 10. Right, x is 10, x is 4, x is 0. So concave up, 0 to 4. I'll write this in interval notation. We have x is in the set 0 to 4, and it's not concave up anywhere else because the rest is negative, but it's concave down. Everything before x, well, I'll just define this as x is equal to maybe -6. So concave down, -6 to 0, and 4 to 10. Notice that I'm not including the points 4 and 10 and -6 and 0 because these cannot be classified as concave up and or concave down, because at x is 0, it changes from negative to positive. This is when it changes from concave down to concave up. But we do not know whether that point at x is 0 would be part of the concave up part or the concave down part. So it's just defined as a point of inflection. It's neither concave up or concave down. Now going to increasing and decreasing. Increasing, decreasing. So it's increasing when f of x is above 0. F of x is in green. So above 0, I'll just define this as x is -3. And then I would define this point right here as x equals 1. I know it's kind of messy. This is x is equal to 3. And that should be enough. Okay, so when is f prime of x above 0? It's above 0 here at -6 and at -3 till -3. Then it goes negative. Well, I'll just include that right here. -3 to this point. I'll call it x equals 2. So it's negative from -3 to 2. And then it becomes positive again from x is 2 or x is 3 to x is 10. So I know this is kind of messy, but you get the point. All right, so we've all heard of continuity, but now we have a new definition, differentiability, new word. So differentiability is a bit different. Let's go back to continuity. Let's try to remember what that is. Continuity has a formal definition, as you could call it. So step 1 for proving continuity is see if the limit as x approaches a, this is continuity at point A, of f of x exists. So this could be done by either doing direct substitution, see if it works, or using one-sided limits. Step 2 would be seeing if f of a exists. And step 3 is if the limit as x approaches a at f of x is equal to f of a. If all of this is true, then the point x equals a, that point in the function, that's continuous. So now differentiability is kind of similar. Differentiability is basically, I'll just do differentiability at x equals a. This is basically step 1, see if it's continuous. So continuous at x equals a. Step 2 is to see if the limit as x approaches a in the derivative function exists. So this could be done by taking the one-sided limits. So limit x approaches a from the negative side is equal to limit x approaches a from the positive side. And if this is equal and the function is continuous at x equals a, that means x is equal to a for f of x, that point is differentiable. All right, so now we'll just see differentiability on this graph. So is this function differentiable at x equals, let's say, -5? Well, clearly we can see it is because 1, it is continuous just by looking at the graph, and 2, this the derivative function, the derivative function also matches, it exists. There's no hole there, there's no anything there really. But at -3 there's a hole, it's not continuous, so it's not differentiable. And then over here, If I wanted to find differentiability at x equals 2, this would not be continuous. Why? Because the one-sided limits do not match. As you can see here as well, there's a jump. And then finally at x equals 8. Well, it definitely is continuous, right? You don't have to lift your pen up when you're drawing this. But here's the problem. This is something called a cusp. And this is when there's a sudden jolt or a sudden change in the function. If we try to draw a line representing the derivative of x equals 8, we can draw an infinite number of lines tangent to the point at x equals 8. I'm going to draw 3 right now, but there are an infinite amount that go through the point x equals 8. So let's test the second rule for differentiability then. We know it's continuous, but clearly it's not differentiable, or maybe it is. So if we look at the derivative function, right, I'll just draw a small sketch for this part specifically. It gets close to 0. I think it goes from positive to close to 0. So something like this maybe. I'll do this in white. And then a sudden jolt, and it suddenly becomes much higher. So it suddenly goes maybe here, and then increases from here. Well, clearly, this is not continuous at all, right? The limit as x approaches 8 for the derivative function, this does not exist. Here we have this, and here we have this. So that means this is not differentiable at x equals 8. So all the points where it's not differentiable that we've noticed, x equals -3, x equals 2, and x is equal to 8. This is when it's not differentiable. Alright, so this problem is asking, is it differentiable or not at x equals 2? Here's the graph. Usually this only matters for piecewise functions, but here's the graph. Here we can see that this is not differentiable at all, like not at all. But we have to use the formal definition of a differentiable function. I don't know if that's what it's called, but we'll do that. So step 1, test if it's continuous. So that's basically the limit as x approaches 2 from the negative side, f of x is equal to limit as x approaches 2 from the positive side, f of x. Well, clearly not. This is 4, this is -2, thus this is false, so not differentiable. Alright, so this is a similar problem. See if it's differentiable or not at x equals 2 still. So let's do that. Step 1, test if it's continuous. Right, do the limits exist? X approaches 2, f of x. Let's see. 2 from the negative side, looks like it's -2. And then limit x approaches 2 from the positive side. This is, yep, -2. Right, both the positive and negative side match. So that means limit as x approaches 2 of f of x is equal to -2, which exists. Step 2, does f of 2 exist? We could just use the piecewise function for this. F of 2, we just have 2 squared minus 6, which is -2. Yes, this exists. And then 3 is limit as x approaches 2, f of x, the same as f of 2. Yes, it is. -2 equals 2 the last time I checked. So yeah. And lastly, we need to check for the actual differentiability part. So we can just write the slope of this, right? The slope function. We know, I'll just rewrite it in blue. This will be our new piecewise function. We have derivative of negative x is just -1 using power rule. So this is in the range -infinity to 2. So I'll just write this in interval notation. And then here we have x squared minus 6, derivative of this is just 2x. And then we have 2 to infinity. We have 2 to infinity. Okay, so we want to find if it's differentiable at x equals 2. So we could just take the one-sided limits. Limit x approaches 2 from the negative side. F prime of x would equal, well, the left side is just this part, so this is -1. And then limit x approaches 2 from the positive side. This is the positive side, 2x of f prime x is equal to 2 times 2, which is equal to 4. Okay, wait, so -1 does not equal 4. That means this is false. So that means this function is not differentiable at x is equal to 2. So we had to go through all 4 of these steps, and the last step we found out it's not. And as I mentioned before, this thing is called a cusp. This is when the derivative changes very dramatically, very, very quickly. So here we have a slope of -1, and it suddenly went to like here. All right, so that's it for this unit or chapter. And if you have any questions, put it in the comment section below and we'll answer it.